Hello, this is Lab 4 for Physics 2211. So the purpose is to observe an object oscillating through the use of a spring, used in a physical experiment and a computational model, and analyze the energies associated with the oscillating spring. So the principles in use, we have the law of conservation of energy, potential energy, kinetic energy, and then the kinematic equations of velocity and position update. And so the initial conditions are the mass of the ball, which was given from the video of the pre-lecture video from that experiment. And then so the initial position that I calculated was this right here. And then we have the gravitation here on Earth, and then the spring constant and the relaxed length of the spring, again from the pre-lecture video. And then this just describes the spring and its equations. L equals the boss position minus the spring position, and then how to find L hat, and then S equals the magnitude of L minus L naught. So the application of forces is the time that the video took, and then the forces acting on the ball were the force of gravity, which just acts in the y direction, and then the force of the spring, which is negative k times S, which we found in the previous slide, times L hat, again from the previous slide. And then the net force is just both of those added together. So these are the kinematic equations, the velocity update formula, and then the position update formula for the ball. And so the initial conditions for energy were delta E equals work plus Q, which is thermal energy, but this experiment doesn't really cover Q, which just leads it to equal 0. And then if we make everything, the spring, the object, and Earth as part of the system, and create no surroundings, work would also equal 0 since no surroundings are acting on the system. And so if both equal 0, then delta E equals 0. And so the conclusion is that since there's no change in energy of the system, whatever the initial kinetic energy and potential energy equal would be also the final kinetic energy and the final potential energy combined, since nothing else is acting on the system to change these values. And so here are the equations. K equals 1/2 times mass times velocity squared, so we just put that in with the values of the ball. And then the same goes for potential energy of gravity, 1/2 times mass times the y position. Then for the spring potential energy, we do 1/2 times k times velocity squared, and again delta E equals work plus Q. And so we just put all of those in. And so here we do the calculations for energy, more in depth again. The mass times the velocity squared, and the mass times gravity times the position y, and then the same goes for the potential energy of the spring and delta E. And so here are the results of the computation. This is for the positions of the x position and the y position versus time. The red is the experiment done with the video tracker, and then the blue is the ideal model. And you can see there's a bit of discrepancy within each, specifically in this area and down here in the y position. And so possible errors are the incorrect initial position when I used the tracker, and slightly inaccurate plotting of data that kind of didn't follow the ideal model. And then the oscillation period, you can just figure out by either taking multiple oscillation periods and then just dividing by how many there are, dividing the time that it took to do those oscillation periods by the number of periods it took, or just doing a single one. Here I just took the average out, and for the x direction it was around 1.67 seconds, and the y direction 1.5 seconds. And so the results for the energy, delta E equals 0, so it checks out the law of conservation and satisfied. Delta E remains 0 throughout the period of the experiment, and as the kinetic energy increased, the potential energy decreased, since they're supposed to equal 0. And yeah, that was it for this one. Thank you.